Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome back. It feels like it's been a long time. Anyway, it's only been 2 weeks. We are talking about energy conservation today. The concept of conservation of energy, which is actually quite an easy topic. All we need for this is just to realize that energy cannot be created or destroyed, which is one of the fundamental laws of physics. So energy cannot be created or destroyed, matter cannot be created or destroyed, and mass cannot be created or destroyed. Once you know that, then you can basically solve any problem, because you know that then energy can only be passed from one form to another and cannot be destroyed. Okay, let's get on with it, because I really don't want to make this long. So here we have a problem. Suppose a person with a mass of 58 kilograms jumps on a trampoline and compresses the fabric a distance of 40 centimeters. How high will the person then bounce above the rim of the trampoline if the spring constant of the trampoline is 1,250 newtons per meter? Okay, so here's the problem. So we have a trampoline, and the trampoline has been compressed because there's a person on it, and that person has a mass of 58 kilograms. Okay, so we're back to testing my drawing skills, obviously. The compression of the trampoline is about 40 centimeters. So what do we know? We know that in this case, all the energy is stored as elastic potential energy. And elastic potential energy is going to be converted to kinetic energy, and is going to be converted to gravitational potential energy. They want the height that the person is going to bounce above the trampoline. So they want the final height, which is, I don't know, maybe somewhere around there. So that person is going to bounce above the trampoline, and they want to know how high they're going to bounce. So one way to solve this is by working out the EPE. So step one would be to work out the elastic potential energy, which is going to be half times K times the extension squared, or x squared. So E is used for extension, but x can also be used for extension. So that's going to be half multiplied by 1,250 newtons per meter multiplied by 0.4 meters squared. Now make sure you convert the 40 centimeters into meters. Okay, and that will give us a number which is going to be 625 times 0.4 squared, which is 0.16, and that's going to be 100 joules. So what do we do afterwards? What we do afterwards is we convert that into GPE. We know that we try to find the height. So step two would be to find the height. Excuse me. And we know that GPE has height in it. So GPE, the maximum gravitational potential energy, is going to be equal to 100 joules. So that's mgh, which is the formula for gravitational potential energy, is equal to 100. So it's going to be 58 multiplied by 9.81 multiplied by the height, and that's going to equal 100. Therefore, the height is going to equal 100 all over 58 times 9.81, or you can use shift solve for that. Okay, so 58 times 9.81, and that equals 0.176 meters. 0.18 meters will do. Okay, that's how you solve that one. Let's carry on. So that's only about 20 centimeters. They've only jumped up past the rim about 20 centimeters or 18 centimeters. Right, let's move on. An 850 kilogram roller coaster car drops from rest at the height of 110 meters along a frictionless track. What is the velocity of the roller coaster along at the top of the second hill? Right, okay, which is only about 75 meters high. And they want the average force required to bring the car to a stop along the 150 meter stretch of horizontal track at the ground level. Okay, so let's have a look. So we have quite a few things to do here. The first thing I need to do is I'm going to draw a very quick illustration because it helps me understand what's going on. Okay, oops, that last bit was quite bad. Here we go. So we have a roller coaster car here, and it has a lot of gravitational potential energy at this point. Now what happens is, obviously, energy is conserved. As soon as it starts moving, some of the energy will be converted into kinetic energy. And then over here, it's going to have a lot of kinetic energy and less gravitational potential energy. And as it goes up again, it's going to have more gravitational potential energy and less kinetic energy. And then down here, all the energy is going to be converted into kinetic energy, and there will be no gravitational potential energy because there's no height. And in fact, what I'm going to do is I'm going to pause this video and find that simulation. Just a second. Okay, good news. I found the simulation, so I'm going to try and show you what that looks like. So here's the ramp, here's the first hill, and then we're trying to make it so that it's as accurate as possible. Here we go. This is the situation we have pretty much. Now I want you to keep an eye on what's going on here. You can see that the total mechanical energy doesn't change, but the gravitational potential energy changes into kinetic energy, and then it changes back to potential, and so on. So let's see what's going on. You see that? So as the car starts rolling down, the gravitational potential energy is converted into kinetic energy, which is what we expect to see. And then down here you have quite a bit of kinetic energy, less gravitational potential energy. As this starts moving up again, what do you expect to happen? What you should expect to happen is that gravitational potential energy is going to pick up again. See? Yep. And then you've got a lot of gravitational potential energy, less kinetic energy, but it's still moving, so you still have kinetic energy. And then down here, what you get is kinetic energy, no gravitational potential energy whatsoever. But notice at every single step along the way, the total of potential energy and kinetic energy always added to the total mechanical energy, or the total energy of the system, which is what this topic is about. The energy is conserved, and that's how we can solve these problems. Okay, let's get rid of this. Okay, so now that we know what's going on, the first step would be to work out the gravitational potential energy. So find GPE. Okay, so we know that GPE is equivalent to mass times gravity times height. So that's going to be 850, 850 multiplied by 9.81, which is the acceleration towards gravity, multiplied by the height of that first hill, which is 110. That's 110. This one here is 75. Yeah. So that's going to equal 850 multiplied by 9.81 multiplied by 110, and that's going to give us quite a big number, 91723 joules. That's how much gravitational potential energy is there to begin with. Now step 2 would be, in order to find the average velocity, do they want the average velocity? Yes, they want the velocity. So it's a two-part question. They want the velocity over here, and want the force that's needed to stop it, to stop the coaster over here, over the distance of 150 meters. Okay, let's keep going. So they want the velocity. Now, what do we know? We know that if we subtract the gravitational potential energy, the first gravitational potential energy we found, which is over here, GPE1, that's going to equal the gravitational potential energy on top of the second hill plus the kinetic energy of the cart, whatever that is, on top of the second hill. So what I want right now is the velocity, and the velocity is in here. Okay, so what I can find is, if I find the second gravitational potential energy and then I subtract that from that, I can isolate kinetic energy. So what I mean by that is this. So kinetic energy is going to equal GPE1, which is the total gravitational potential energy that we worked out at the start, minus the second GPE, GPE2, which is what we find over here. So there's another bit of GPE here. And this one is going to be slightly different because the height is different. Another way you could do it is just going like the height, the first height minus the second height. But I like to do it the long way just so my students understand. So that's going to be 917,235 minus the second GPE, which once again is MGH. So that's going to be 850, same mass, same acceleration towards gravity. The only thing that's different is, of course, the height, which is 75 this time. Okay, so 850 multiplied by 9.81 multiplied by 75, and that gives me, just check your answer, because if you're doing this along, you can check your answer and see if you get the same answer as me. And so the answer should be this. Now, I did do this in class, but this is just in case you want to do this again. So now I know what the gravitational potential energy is, what the kinetic energy is. So what I can do is part 3, I can find the velocity, which is going to be the kinetic energy basically. So kinetic energy is equal to half mv squared I don't find fasting hard, alhamdulillah. I find fasting easy. It's just that I feel like my level of concentration is less. So I'm sorry if I'm making mistakes. 291, and Ramadan Mubarak, by the way. 847.5. Okay, so you can use shift solve, or you can use that. 291,847.5 all over half times 850. Okay, so divided by so it's approximately 26.2 meters per second. Now we're not done solving the problem. There's only one last step to go, because this part here is asking for the average force required to bring the car to a halt or to stop it completely. Now we know that work is equal to change in energy, and so remember how much energy the cart had at the start. So over here, let me just use a different color. Over here, that's the total energy of the system. And how much energy did the cart have? It had 917,235 joules. Now over here, it's going to have the same amount of energy, right? Because energy cannot be lost or destroyed. So in order to stop it, the work done has to be equal to the amount of energy. So that's why I wrote that. So now we can solve for the work done. We know that work is equal to force times displacement. And so we know what the work is going to be. So the work is going to be equal to the energy. We don't know what the force is. That's what we're trying to find out. But we know what the distance or the displacement is going to be, because that's going to be 150. That's a constraint from the engineers who designed this roller coaster. They said, okay, so it's 150. How much force do we need? And so F is going to be 917,235 all over 150. 917,235 divided by 150, which is 6,114.9 newtons. Okay, that's the answer to that one. Right, moving on. A 750 kilogram roller coaster drops from rest at the height of 90 meters along a frictionless track. If the coefficient of kinetic friction due to braking along the horizontal track at the end of the ride is 0.720, over what distance does the car need to brake to come to a complete stop. Okay. So once again, it's the same scenario, except this time they're not looking for the velocity over the second hill. They're just looking for the distance. They want the distance at the end, how much distance is needed. We can work out the force because they're giving us the frictional force. So friction is equal to mu multiplied by the normal force. And that's it. So 2 steps really. So step 1, find GPE. In this case, gravitational potential energy is going to equal mass times gravity times height, which is going to equal 750 multiplied by 9.81 multiplied by 90. And that's going to equal, let's see, 750 times 9.81 times 90. And that's going to equal 662,175 joules. That's how much gravitational potential energy we have. That's how much energy the system has to begin with. Now the next step would be to just find out, because we have the change of energy, and so we have the work, right? Because it's the same as the change of energy. So we can work out. Let's find the force. Find the force first, which is going to equal. We're looking at frictional force here, 0.720. That's from the question, right there. And then the normal force we're going to have to work out. Normal force, if you remember, is going to equal to mass times gravity. So that's going to be 750 multiplied by 9.81. 0.720 times 750 times 9.81. So we've just worked out the force. So we have the force and we have the total work. So we can work out the distance. So the distance is going to be the work over the force, which is going to equal 662,175 all over 5297.4. Which is 125 meters. Okay? And if you need a bit more help with this, just go back and watch this, or send me a message. I can explain this to you. It's just that I'm trying to keep this video as short as possible. Okay, a person with a weight of 52 kilograms walks up a flight of stairs to a takeoff point of a bungee jump. Okay, so here we go. We've got stairs all the way going to a bungee jump platform, which is 3.1 meters high. Okay, and they are over here and they're looking over and they're about to jump. I've actually done this, by the way. I've done a bungee jump. Very scary, but fun. Okay, and so they're going to jump. So that's 3.1 meters. What are they asking for? They're asking for how much time would it take. Okay, so we know that power equal to energy over time. Okay, another way you could write this if you prefer is P equal E over T. So what do we have? We have the power. We need to work out the energy, how much energy they're going to have up there. So it's going to be GPE, isn't it? They're going to have a lot of GPE. So it's going to be, find the energy first. Find GPE, which is going to equal mgh, which is 52, multiplied by 9.81, multiplied by 3.1. Simple multiplication, really. So 52 times 9.81 times 3.1, and that equals 1,581.4 joules. That's how much energy they have to begin with. And yeah, and then what we're trying to find, how much time does it take to climb the stairs with exactly 200. Oh, I thought they were going to ask about the chord and the elastic potential energy and whatever. They just want to know how much it takes for them to climb the stairs. Okay, so we've just found the gravitational potential energy they have. When we have the power, so which is 250, so time is going to equal energy over power, which is 1581.4 divided by 250, which is approximately 6 point something seconds. Yeah. Okay, moving on. Oh, here we go. So now we are doing some revision questions for the quiz. Let's go. I would highly advise that you try and do these yourself before I answer them. Which statement best describes the principle of conservation of energy? Energy is created and destroyed. Of course not. Energy is not created or destroyed. Energy can be transformed, but the amount of energy, the total amount, remains constant. A car reaches the highest point of a roller coaster at this moment. It has, at the highest point of a roller coaster, the highest point, okay, if we can reset this, you can see what I mean by that. So let's reset it. Highest point, it has a lot of gravitational potential energy. As it starts moving, what happens at the lowest point? A lot of kinetic energy. Okay, so that's what happens. So at the highest point, it has the maximum gravitational potential energy, the minimum kinetic energy. Oops, sorry. So that's the answer. A 3.5 kilogram object is dropped from a height of 8 meters just before it reaches the ground. Its kinetic energy is approximately what? So GPE is going to be converted to kinetic energy. So if we find GPE, we can find the kinetic energy. So it's going to be mgh, or 3.5 multiplied by 9.81. I'm not going to do this for every single question. I just want to show you where I got it from. Okay, that's how you do it. 3.5 multiplied by 9.81 multiplied by 8. And that's going to be 275. Please don't forget to multiply by 9.81, because some of my students will go 3.5 multiplied by 8, and that's 28. So that's the first one. So that's definitely wrong. It's 275. Okay, number 4 says a cyclist starts from rest at the top of a hill and moves downwards. What happens to their energy? Of course, it's going to be converted from gravitational potential energy. So that's B as well. Next, a diver jumps off a diving board at the halfway point in their dive. Their energy is what form? At the halfway point. Okay, that's interesting. So they've jumped from here all the way to the water, and at the halfway point, their energy is going to be GPE, because they still have height, and kinetic energy. So it's going to be half kinetic energy and half gravitational potential energy. So in fact, it's not going to be just kinetic energy, it's not going to be just gravitational potential energy, it's going to be both. And at the halfway point, it's going to be exactly both, almost, if we ignore losses to thermal energy. Okay, a stretched rubber band is released. The energy transformation is what? Well, that's obviously going to be elastic potential energy to kinetic energy. And it's the only option that actually makes sense. All the others are just weird. Which of the following correctly describes mechanical energy? So mechanical energy, as we said, is the total energy. So if you look over here, that's mechanical energy, and it's the total of kinetic and potential, right? So if we reset this, look at this. Initially, it's potential, which equals mechanical. Then as we go down, the total of these two equals that. Okay? The total of these two equals the mechanical energy. So the mechanical energy is the total of, it's the total energy. It's both potential and kinetic. So it's the sum, or the total, of kinetic and potential energy. A bungee jumper reaches the lowest point of the jump. The energy is mostly in the form of, at this point, it's going to be mostly in the form of elastic potential energy, and then they're going to bounce back up. So the bungee jumper jumps, and then it stores the energy. That elastic rubber band or rope stores the energy, and then they spring back up. So at this point, it's going to be elastic potential energy. There's some energy in gravitational potential energy, as well as maybe a bit of kinetic, but it's mostly elastic potential energy. A 5 kilogram object is lifted 2 meters above the ground. The gravitational potential energy gained by the object is going to be 5 times 2 times 10 approximately, because it's 9.81, so that's going to be 100 joules. A roller coaster is at the bottom of the loop. At this moment, it has what? So at the bottom of the loop means it's over here. So at this point, near the ground, it has a lot of kinetic energy, almost zero gravitational potential energy. Okay? Maximum kinetic energy and minimum potential energy is what it has. A ball is thrown vertically upwards. What happens to its energy as it moves up? Well, the ball is thrown up, and let's ignore the down part. Okay, let's just say it's thrown up. So this is the ball. Of course, as it gains height, it's going to gain gravitational potential energy and loses kinetic energy. So that's what's going to happen. Kinetic energy is going to decrease. Gravitational potential energy is going to increase. So it's B. Which of the following best describes work done on an object? Work is equal to force times displacement. Work is transferred. Energy transferred when force is applied over a distance. Yeah. Remember that work is also equivalent to the change of energy, and so that makes perfect sense. Right. Moving on. An object is pushed across a rough surface. What type of energy is produced due to friction? Thermal energy. So there's a lot of heat energy being produced, obviously, when you face resistance. A spring is compressed and then released. The energy transformation is what? Of course, that's going to be elastic potential energy to kinetic energy. A pendulum, which is a form of a swinging ball or object. A pendulum, and they swing like that, and so on. To the other side. A pendulum swings back and forth. At the lowest point in its motion, the pendulum's energy is mostly what? Kinetic energy. Because at the lowest point, it doesn't have a lot of gravitational potential energy. It's over here that it had a lot of gravitational potential energy. And then at this point, it's kinetic. And at this point, it's back to gravitational potential energy. Right. Here we go. A 55 kilogram skateboarder starts from rest at the top of an 8.4 meter high slope. Here's the slope. Here's the skateboarder. Okay, not the best drawing. I will admit that. 8.4 meters. Use energy principles to calculate the speed halfway down the slope. So we want the speed over here, halfway point. Now, at the halfway point, what's going to be the speed? Well, it's going to be, let's first of all consider the energy. The energy at this point is all GPE. The energy at this point is all KE. At the halfway point, the energy is going to be half KE and, well, I shouldn't say half. I should say KE and GPE. Of course, in equal amounts. They should be halves. So what I'm going to do is I'm going to calculate using GPE. I've got the height. I'm just going to calculate half the height, and then I can find out what KE is because it's exactly the same. So the velocity is going to be find GPE at 4.2 meters, which is halfway point. So that's going to be 4.2 multiplied by 9.81 multiplied by 55. Two, 6.11. That's how much energy we have, and that's equivalent to half mv squared. So I can work out what v is going to be. So step 2, find v. So v is equivalent to total energy divided by half of m, which is just the same as this. Kinetic energy equals half mv squared. Okay, so I'm just taking shortcuts here. 2,266 all over half times 55. And the square root of that, so it's going to be 9.1 meters per second. Right, moving on. A 2.5 kilogram ball starts from rest at the top of a 5 meter high hill, assuming no friction. Okay, this time it's 3 meters sorry, 5 meters high. And they want the speed at the height of 3 meters. So that's about there. They want the velocity at this point. Well, so once again, the velocity at this point is going to equal the height. So let's find out GPE, find GPE. Just going to be careful here. You're not going to go 3 multiplied by acceleration towards gravity multiplied by the mass. Because even though it's mgh, you got to work out what h is going to be. H is going to be this height here, which is 2. Okay, so it's not going to be the 3. It's not going to be this height here. I've explained this in class, but I hope you remember. So that's going to be 2.5 multiplied by 9.81 multiplied by 2 meters, because we're looking at this height here. So that's going to be 2.5 times 9.81 times 2. It's going to be 49.05. It's always a good idea not to round at this stage. We only round at the end. So now we find velocity. Find v, which is going to be, so first of all, ke equals GPE. Oops. 2 meters. So we've just worked out at, so we have v squared is equivalent to 49.05. I really don't need to do all of this, do I? I'm just going to solve it, and you can solve it. And if you have any problems, you can always ask me. 0.5 times 2.5. So it's about 6.26 meters per second. Okay, let's keep going because I really want to save time here. I want to keep this under 40 minutes. A 900 kilogram car is moving at 6 meters per second when it collides with a spring barrier with a spring constant of 400,000 newtons per meter. Calculate the maximum compression of the spring. So here's the situation we have. We have a car that collides with a spring barrier. Okay, and what they want to work out the compression here. Okay, we don't know what that is. We know the mass of the car is equivalent to 900 kilograms. And do we know the speed? Yes, the velocity is equal to 6 meters per second. So we've got everything we need. In this case, we can solve the kinetic energy. So 1, find Ke, which is going to be equivalent to half mv squared, obviously, which is 9,450 multiplied by 6 squared. So that's going to be 16,200 joules. And then step 2 would be to find the compression. We know that step 2, the elastic potential energy, assuming all the energy has gone into the has been converted from kinetic energy to elastic potential energy. So all that energy is going to be converted into the kinetic energy is going to be converted into elastic potential energy. So that's going to be 16,200 joules is equivalent to half Ke squared or half Kx squared. So just using some simple maths really, divided by so the compression is approximately E is equivalent to 0.28 meters, okay, or about 28 centimeters. And I think this is the last question, guys. We've made it. A 5 kilogram bowling ball is dropped from a height of 2.5 meters. 2.5 meters, and it's a bowling ball onto a trampoline. So here's the trampoline. Okay. Does it have a mass? It's 5 kilograms. The trampoline acts as a spring with a spring constant and blah, blah, blah. No energy loss. Calculate the maximum compression. Easy. So what we need to do is step 1, find total GPE, which is GPE at the beginning. So that's going to be mgh, which is going to be 5 multiplied by 9.81. I'm almost writing like I do in the classroom suddenly. Times 2.5. 5 times 9.81 times 2.5. That equals 122.6 joules. Remember how I said it's not a good idea to round at this stage, so I'm just going to do that. And then step 2, find compression. And that's going to equal half kx squared or half ke squared. It's up to you what you like, really. 122.625 half multiplied by 15,000 multiplied by e squared. So therefore, E is equal to I got 0.13 meters, or about 13 centimeters. Thank you very much. All the best. I'll see you in the next one. Ramadan Mubarak.